Hello, everybody, and welcome to the Developing Computational Skills in the Sciences with MATLAB webinar offered by SERC, MathWorks, and NAGT in collaboration with each other. Today we'll be reviewing with you some tools that will help you teach computational skills, not so much for you, but more because as educators, your goal is to teach your students how to do the science, the domain that you're focused on, and you want to do it along with some computational skills. And so using MATLAB and other tools that we'll be sharing, we'll be conveying to you some ideas of how to go about that. And with me today are four educators in sciences, Alan, Ben, and Daniel, and they'll be sharing with you some information as well. So first, we'll be talking about strategies or during the course of the talk. And the idea here is that we've seen that there's a lot of interest in data analysis. Sometimes you need to teach modeling. And at the same time, you need to teach computation or essentially programming. And you have to teach the domain concepts that are related to your science. So how do you do that? Because that's a lot to try and accomplish in a class. Second, we'll be sharing very specific resources that can help you do this. And by resources, one of them we'll be showing is teaching activities, which are kinds of modules that you could actually use for a single class and with code so that you could use that actual code and those actual instructions for your course. There are some tools we'll be discussing that help you learn about how to teach computation, meaning the actual programming piece, which by itself is hard. And these are all based on MATLAB. So you'll see how to apply it with the actual MATLAB code and teaching MATLAB in your course. And finally, by virtue of this webinar and also by some resources we'll show you, you'll have access to a larger community of peers who have been doing this and who have been developing materials. And you ought to be able to take advantage of them once you're getting into this, thinking about how you're going to teach computation better. You can reach out to them for more insights. Okay, so before we move on to the specific activities, of which there are 3 that we will review, I'm going to take you through a tour of some of the resources that are available for teaching computation in the sciences, and in particular those resources that are housed on the SERC site, and you'll see what I'm getting at in just a second. Before we get to the resources, I want to give some background on how we got here. There was a workshop back in October called Teaching Computation in the Sciences with MATLAB. And the idea of this workshop was to get faculty who have in common the goal of teaching computation and using MATLAB, and to have them share their best practices. You might think that by a workshop you would have MathWorks people stand up and talk about MATLAB, or different people standing up and talking about MATLAB features. In fact, the focus was much more on the teaching and the tools that you need for teaching, and less about a feature list. And so the process was that the participants who came talked about what they'd learned, both things that worked and things that didn't work. And together we built a set of best practices that we could then share with other people like yourselves after the workshop. And so the outcomes were these best practices. And you can see here the workshop invitation. If you're interested, you could certainly go to the website and look at that. Specifically, the content from the workshop is there, meaning that if you wanted to review what we did, you could look at some of the presentations, you could see what the structure of the workshop was, and you could perhaps get some of what we got from being there without actually having attended. So it's there if you're interested. Also, you can see who was there, and not only do you have their names and contact information if you want to reach them, but they also have some things that they submitted in advance of the workshop. These are often these activities I mentioned, or courses or other things. And so you can see what each of these participants provided as part of their workshop inputs to help us develop a workspace or a website that would be available to other people to use what they've developed as part of their teaching experience. Okay, so there are 2 main resources that I'm going to be sharing that, with the idea that you'll then know that it's available, and also hopefully you'll go back to it after this webinar. First, there's the MATLAB resource page for educators, and here's a picture of it, and you can see further down, I will take you to it shortly, that there's a whole long list of resources that are available on that page. And the second thing I'll be sharing is the outcome from the workshop, the main website that talks about how do you teach computation in the sciences. And on that same page, if you continue down, you could link to the specific artifacts or specific teaching tools that you could use, including activities, and read some essays from other people. And there are also some courses on the site as well, and I'll be showing you how to access those during the demo. So coming to this link page, you can see where the resources are, and I'm going to now get out of the sorry, I'm going to stop sharing my screen here. Sorry, I'm going to stop looking at the webinar now, and I'm going to switch to a mode whereby I'll be showing you my actual desktop. So I'm sharing my screen. Okay. But I do have to bring this up. So now I'm bringing up the this page. So hopefully you can see it. Rory, can you see?
Yep, looks good.
Okay, so this is that page I was talking about. This is the MATLAB resource page. If you're not familiar with MATLAB, you might want to read through the beginning piece and get a sense of what MATLAB is, maybe read a couple of articles about how MATLAB is used, in this case in particular in geoscience. If you are familiar with MATLAB, then you'd be less interested in that information, but you may not know things like that there's an auto-grading program that you can use with MATLAB. And just like if you wanted to have your students write code but have their problem sets automatically graded, you could set that up in Cody coursework, and then you wouldn't have to do the hand grading of the code. So that's an example of a resource. But moving down to the resource section here, there's a lot of things here. Whole courses. If I went here, I could find courses from actual other professors, and they have them posted. Some are on the SERC site showing you what they teach in their class. Another resource is this MATLAB Recipes for Earth Science, which is actually based on a book, but is actually a website. And so if you come here, you see there's course materials and information about interacting with hardware and other things. The author, Martin Trauth from University of Potsdam in Germany, he actually has a blog that he posts to talking about how to use MATLAB. So he has teaching resources. If you keep going down, you see the section called Code Examples. This little one-liner here, MATLAB Product Code Examples, actually takes you to the MathWorks site, and it brings you to all of the code examples that are available in MATLAB. So you can see here on the side not only MATLAB, but maybe you wanted to learn about statistics and have some examples that you could build on for teaching for that, or image processing, or computational biology. So there are many things that you could get access to that might be sort of like a starter kit for you to get yourself started on your activities, but also get students going. And finally, similarly, the same thing's true for videos. Any of these videos could be provided to students to get them up and running. Maybe they don't know how to work with arrays in MATLAB, and just in a few minutes you could get them going. So that's the resources page. So again, that might be a good place to get started thinking about some of the tools that are available and how to set up your course. But getting to that next thing I talked about, the Teaching Computation in the Sciences site, that's this here. And you can see it sort of starts out by explaining why computation is important in the sciences. And then, based on the workshop, we ended up with 4 different topics that the attendees thought were important. Data analysis, modeling, building self-efficacy, meaning students getting comfortable with computation, and how do you do this across the curriculum. And so if we pick, say, data analysis, I'll dig into that and show you what these subpages look like. So it talks a little bit about why data analysis is important, and again, this is based on the input from the participants. And then here you see that we had a couple speakers. One of them is speaking here today, Daniel from MIT, but Janelle Hanrahan, also from Lyndon State College, had a great talk about how students can learn to analyze temperature, and she has them download NASA data, and using some analysis techniques helps them to figure out how to create the same baseline, and based on that figure out whether temperature has been rising or not over time. And in the end, they create the exact same visualizations that NASA created using some of those same assumptions. And so it's great, and you can go here and just see what happened at the workshop and read about it and maybe build tools based on what you see from other educators. Now, I said that you can learn this from the slideshow. If you go to the Teaching Activities collection, here, let's say you did want to learn about what Janelle taught in the class. So I could type in Janelle. I'll use that because I know I can maybe find it that way. And so you didn't see, but there were 46 teaching activities. This is one, and it says Analysis of Global Temperature Trends. And in fact, this isn't a slideshow. This is Janelle describing to us how she goes about teaching global temperature trends and analysis. And so this is fairly short, but here's the activity handout, which I won't click on now, and that's what explains to you what this teaching activity is really about. How would you invest a class or two, meaning an actual like 1 or 2 hour class period, in, it says here 2 hours completion time, right? And it's a lab. So she's giving the students an activity to do as part of her course. And I said that there were 46 activities. So so if I wasn't just searching on Janelle, I would see all 46, and there you go. So any of these may be of interest to you, and you might want to peruse them. You see here it's on the nav also. Okay. All right. So so that's data analysis. You saw that there were separate sub-sites for each of these different topics. You could go to any of these. Now, other things we often get questions about are these general capabilities. You may hear during this that there's something called a MATLAB on-ramp. That's a great way to get your students started. MATLAB Online is a cloud-based version of MATLAB, or MATLAB through a web browser, which is centrally located so that students can all have a similar experience. There are more, I mentioned Cody Coursework, so there are some general resources that are also made available via the site that would be true regardless of which subtopic you were trying to teach. And that's another set of things you could peruse by coming here and clicking on the links. Okay. So now I'm going to go back to the presentation mode. Okay. And we'll bring the slides back up.
Yep, getting them right now.
Okay, so this is what I showed you. We went to the resources page for MATLAB. Then we went and looked at the website that was created from the workshop, including some of the subsections and some of the general tools that are available. And I encourage you after the webinar to go take a look at these sites and see what's there, peruse, go deep on the things that matter to you, because that's really where all the meat is, right? But before you do that, we'll now move on to the 3 activities. So I mentioned teaching activities. Now each of our presenters today will show you an activity relevant to their discipline. Alan will go through one in geophysics, Ben will go through one in biology, and Daniel will go through one in neuroscience. You'll get a flavor of what it looks like when different disciplines and different professors cover computation in their class, but again, teaching the domain-specific concepts that they want to cover in their classroom. Okay, thank you. Alan, we're ready for you to start.
Thank you, Lisa. Hi, everyone. This is Alain. So I'm going to talk about 2 groups of MATLAB M-files, MATLAB functions that I put online on this GitHub Near Surface Geophysics website. And they're touching on some of the things that Lisa mentioned earlier, for example, data simulation, data processing, but also across curriculum activities. So I'm actually using those groups of MATLAB programs in my Near Surface, Introduction to Near Surface class. But they're all very simple M-file programs that can be used also, for example, in an introduction programming class as an example for data simulation or data processing. So Seismo, the first group that I'm going to present, is simulation of seismic data. And the idea there is that when we're going out to the field, we want to train our students that they don't just go out and measure something and then hope that they can see something from the subsurface, but that they actually come up with an idea of what specifically they want to measure and how can they optimally design their experiment out in the field. And the second group, GPRO, is a ground-penetrating data processing and visualization tool. And even if you don't have a ground-penetrating radar system, which I guess most won't just have one, you can download ground-penetrating radar data from online. And I'm going to show a little bit later a couple of websites where you can do that. So before I explain the teaching activity for the data simulation of seismic data, I want to just quickly, for those of you who may have not seen seismics, quickly explain what the idea is. So what we're doing is we're literally hitting the ground with a big hammer, as you can. Oh, sorry, I gotta show the pointer. Yeah, we're literally hitting the ground with a big hammer, as you can see here, and then a wave will go through the ground, and we'll measure it at these blue little boxes here that are called geophones. And what we're recording will look like this. So on the y-axis here, we have the time that the signal is being recorded. On the x-axis, we have the location along the profile. And for example, here, a hammer blow was at around 60 meters. And as you can see, the wave through the ground arrived first at those geophones that are closest to the hammer, and then further away, it arrived later. And from these waves, we're trying to learn something about the subsurface. And as you can see, it's not just one single wave that moves, but there's a whole bunch of waves that are working together. Now, the waves that we will be able to record are, for example, so this here is the surface, and the blue triangles are the geophones, and the lightning here is where we hit the ground with the hammer. And we have, for example, a sound wave. Obviously, that's just really from the sound of the hammer hitting the ground. That goes with the speed of sound in air. Then we have a direct wave that moves along the interface between the surface and the subsurface. Then we have a reflected wave, if we have an interface. And we have a refracted wave that is moving along the interface with the speed of sound in the lower part of the subsurface. And so refracted wave is actually something that may really help us measure this variable v2, the velocity further down. And these waves will not arrive all at the same time, but this here is a simulation that students can make with Seismo, where they give it an example for v1, v2, and the depth to the interface. And this here simulates arrival times of the air wave, which is the steepest one here, because speed of sound in air is slower than in the ground. Then we have the direct wave, which is the black circles here. Then we have the reflected wave, which are the red circles here, and the refracted wave, which are the blue circles here. So when students see this, they will think, okay, it's going to be easy to tease out these various waves because, well, the arrival times are easy to see, right? They're clearly separated. Blue is separated from black here. But unfortunately, we're not recording arrival times. We're actually recording waveforms. And we can simulate how such waveforms would look like, such seismograms would look like using Seismo. And so I have the students simulate this using, as example, this 1 meter geophone spacing that they use to simulate these arrival times. And this is what they get from Seismo running in MATLAB. So here you can see that it's very, very hard to actually pick which one is a refracted wave, which one is a reflected wave. There's a big jumble of overlapping waves here, and I'm using the Wavelet toolbox to do this. And students will learn from this activity that if they use this spacing, they won't be able to see anything. So I'll have them play around with the only parameter over which we have control, which is the spacing of the sensors, or the length of the profile, if you will. And if they extend it to, for example, 2 meters, then it becomes very clear that we can now suddenly finally see this refracted wave clearly stand out from the reflected and direct waves. So that's a good way of planning our field work before we actually go out and measure something. And if you want to use this teaching activity, it is exactly the teaching activity that Lisa presented earlier on the list of the slides that we have. But I also put it on this GitHub site because I'm constantly trying to update it or maybe load new teaching activities on it. Or if you have some of them, then please use GitHub to upload yours or send them to me. I will share them, obviously, with crediting you. And, yeah, please just make use of it. Oh, Charlie just asks if it works for dipping interfaces. Not yet, but if you want to implement it, that would be awesome. Okay, so next example is GPRO for ground-penetrating radar processing and visualization. Ground-penetrating radar is similar to seismics as it is also a wave-based method, but instead of shock waves, we have electromagnetic waves. And instead of having one transmitter and several receivers, we have one source, which is the transmitter antenna here, one receiver, which is this receiver antenna here. They're at a fixed distance from each other, and we're dragging them along a profile. And this trigger wheel here measures and makes a measurement every couple of centimeters, for example, 10 centimeters. We can choose what we want for that. And this GPRO processing software is, again, very simple MATLAB scripts that your students can manipulate, can play with it, can look into them and see how they actually work. And it does some very basic data processing, and it can do 2D profiles and depth slices. So if you have several profiles that are next to each other, then you can have a horizontal depth slice through them. We can incorporate topography, which can be very important. And there's a whole tutorial documentation with example data. But if you want to work with really cool data, then go, for example, to this USGS Alaska website. They have some really spectacular GPR data. And instead of showing you now an example where my students recorded some data outside on campus and then processed it, I'm going to show you a little bit a more exciting data set that my grad student, Christine Liu, measured just 3 weeks ago in Yosemite Valley. So she's investigating a rockfall deposit at El Capitan. And what I'm showing you here is a ground-penetrating radar profile. The two-way travel time here is on the y-axis, and on the x-axis is the along profile position. And every thin slither of pixels here is a single trace, a single wiggle that we turned into black and white dots. And as you can see here, we have these strong black and white stripes at the top. And these are the airwaves that travel directly from the transmitter to the receiver without going through the ground. So obviously we want to mute this and maybe enhance a little bit what we see down here. There seems to be a little bit something. So a first step could be to just subtract an average trace. So if we average all of these traces and subtract them, then we do get a little bit rid of this airwave, and we do see the subsurface here a little bit more. But what we can do as a next step to enhance the subsurface even a little bit more is we can just apply what is called, for example, a T-power gain, where we increase the strength of the signal with an exponent of the travel time down here. So the further down we are, the stronger it gets. And we can already see quite a bit more. But obviously we want to bring in topography. And as soon as we bring in topography, we see, okay, this here is the surface of this rockfall deposit. But here at depth, so this here would be the Yosemite Valley, close to the road. And then we see that before actually, when the topography goes up to this rockfall deposit, we see that an old valley floor underneath this rockfall deposit continues almost horizontally, but then has some nice, interesting topography. And yeah, this is we find kind of an exciting result. And so far, this data set is not yet part of GPRO, but I'm hoping once my student publishes, and if my student is okay with it, then I'm going to make it part of it, such that you can have your students play around with it, for example. And so the tutorial with some, unfortunately, not as exciting test data, but will get better at some point, is here on this GitHub site. And some really exciting GPR data is on this USGS Alaska website. And just to quickly summarize, or I can even leave the summary up here, so we have those two packages. Please make use of them. They're both available on this GitHub website, and use them for teaching programming, data simulation, processing, or even just as in a near-surface geophysics class. Okay, and that's it. Thank you.
Okay, thanks, Owen. My name is Ben Bratton, and what I'm going to walk you through today is an example of visualization, specifically visualization of dynamical systems. And this is something that I teach in a graduate course for molecular biology PhD students. And it's a 4-week course that we call Biomath Bootcamp. It's 8 hours a day, 2 hours in the morning of background lectures, and then work problem sets in the afternoon. And so this is something that students who are in the PhD program, they typically don't have a lot of previous exposure to scientific computing, and there are some skills that they lack in being successful using that. And they kind of come in three different categories. The students lack some level of competence. They have no idea what it is that they want to do. They have no idea how it is, if they do know what they want to do, how to do that. They lack the terminology and the skills to get either their own code running or even using packages like great packages Elaine just showed us, how to get them to run. They also often lack the confidence to describe their own skills, the things they actually know what to do, or even the confidence to describe what they've done after they've done it. And finally, as those of you who have worked in scientific computing know, there's a lot of grit, a sort of stick-to-itness that you have to deal with. Data is not always pristine. Compilers change over time. New operating systems come online, new technologies, and all these kinds of things lead to a grit that you need to develop as a skill. And so the way we've formulated the problem sets is a way to build them as modules. And these modules are small pieces of code. So it's like a few lines of code, typically with a visual output. And that gives the students confidence to know very quickly whether they're doing something correctly or wrong. And also, they tend to be reusable pieces, so they'll be able to use it on maybe a problem today and maybe a problem in a different week in the same boot camp. And what we really hope is that they'll then be able to come back and use some of these modules that they've written in their own independent research. So maybe it's a module of some type of filter that they're going to do some signal processing with, or maybe it's a module for how to read in files from the web or read in data from some collaborator that they have. And so the particular example that I'm going to walk through today comes from the week that we call Dynamical Systems. And dynamical systems are such where we know how the evolution of the system, sorry, this equation didn't come through quite correctly. This should be x dot, so let me, so this is going to be the dynamics of x, how x is changing with time is a simple function, which we know, and the dynamics of y, so y dot is another simple function. And the question is, how does the system of x and y, does that evolve in time? And it turns out this is very applicable for biology because things that are alive, they do things that are dynamical, like they eat, they grow, they reproduce, they die, they move to new locations and things like that. And so what we've done is we've come up with some situations where the problems teach them the underlying math and the scientific computation tools that they need, but the problems are biological. And so we walk them through an example. In this case, this is of a neuron that fires. We also make up a somewhat fictitious system where instead of the sort of standard rabbit and wolves, we give the rabbits weapons to fight back against the wolves. And so you can look at the population dynamics in the weaponized rabbit and hungry wolf situation. We also take a look at another sort of fictitious example, but this is about populations moving around, and it came from the phenomenon in the late 19th century of people moving from England to the French Riviera. And so the thought is, what can the people in France do to encourage, say, the English to move to Spain instead of coming and taking their resources or giving their resources, depending on your perspective. Okay, so the example I actually want to walk through today comes from glycolysis in yeast. And so this is the dynamical system that's governed by these particular equations. And I'm not going to walk you through all the code, but what I am going to walk you through is the outputs of these different modules. So if you want to see each of the versions of the code as we go along, you can actually check out earlier versions. I think there's about 14 that are up, and it's at that GitHub address there. I'm now going to switch over to my screen. And I'm just going to show you these modules sort of as they come together and describe how we've formulated the questions so that the students know what we're looking for from them. So the first thing that we do is they just need to basically implement the dynamics. And so that means we tell them, take a red dot and move it around the screen in the way that the system would evolve given these dynamical equations. But as you see this dot moving along, it's kind of hard for your brain to remember exactly where it's been. So the next question we say is, add blue tails to see where the system has been. And some students, they love when we tell them exactly what color or shape to make the spots, and some of them are kind of contrarian and just use whatever color they want. Now, there's a point in each of these systems called the fixed point, and that's really where the dynamics are quite interesting. And so then we tell them to calculate the fixed point for the system and move their dynamical simulation to there. We then ask them, move even closer to the fixed point and answer the question, is it a stable or unstable fixed point? So if it were stable, the red dot would be basically adhered to the black X, and all the dynamics would drive it there. But here you can see that it actually moves away from it, so it's an unstable fixed point. Now, exactly at the fixed point, there's basically nothing happening in the dynamics. That's the power of the fixed point, or the interesting part of the fixed point. So we have them add a time indicator to make sure it's not their code that's not running, but that's actually what's supposed to be happening. We then add transparency. In this, we use the function patchline from the file exchange to help them gain skills in learning how to use other people's code, so reading help documentation and implementing it, as well as just exposing them to the huge variety of resources out there for people working in MATLAB. Okay, so then we go back to a core MATLAB function of quiver to look at not only the evolution of a single point, but at every point in space, this tells you how the system would be evolving. And then, it's important for the students to be able to pick a range that they're actually able to see all the dynamics in. And then what they're going to use is they're going to use these modules that they've built to move to a different dynamical system. This time, we've basically just made up one. And the interesting thing about this is it's going to have a couple of different fixed points. So because one of the fixed points is actually a stable fixed point, we tell them to basically restart the simulation after a fixed period of time. And this is basically the last component that they need to make their final visualization, which is going to be multiple points, each of which lives for a different period of time. And so they're able to take these dynamical systems, implement them in MATLAB, and then visualize what that system looks like for various configurations. And here they can see quite clearly the stable fixed point versus the unstable fixed point. So with that, I'm going to switch back over. We'll see if we can switch back over. Rory, I don't seem to be able to get my connect window. Oh, here we go. We will stop sharing, and then we can go back to the PowerPoint.
Yep, I'll bring that up.
So these kinds of modules, they're helpful for the students in being able to build some of that grit, some of that confidence, some of those skills, but they're also quite helpful for the instructors as well. And the reason is there's this interesting phenomena that we've discovered over the past few years as we've been offering this course, is students who are new to computing, they don't have an understanding of when would be a good time to take a break. They just don't have a concept of how to break the problem into smaller pieces, and so these modules help them do that. The students also fail in that the code has errors quickly when you're working in modules, but they also succeed quickly. They have that immediate gratification that helps really build their confidence that they do know how to do something. And then it also just encourages them to reuse their code. So all of these things are things that, while we've used them and applied them in a molecular biology context, I think that they're tools that could be implemented in a variety of both levels of teaching as well as different fields. And so with that, I'll hand it over to Daniel.
All right. So welcome, everyone. And today I'm going to be talking about how to apply principal component analysis to do data visualization and classification. I teach scientific computing in the brain and cognitive sciences, and this field of study is usually perceived as a soft science, and most students don't have a motivation or interest in learning scientific computing. And therefore, us as instructors, we need to come with effective strategies to break the ice and to cope with that inertia. And an interesting way to do that is to tailor problem sets and activities that make the things that they're going to learn relevant and transferable to different contexts. So today I want to showcase a couple of examples on how to do that effectively. So for that, we use what I call a two-tier approach. The first tier is we give them an opportunity to learn the basics by playing with toy examples. And basically, we ask the students to build either modeling or visualization by building it step by step. And by that, I mean that they're not going to use canned functions or tools that are available, but they're going to have to go from the math to very simple functions that they can implement in MATLAB. And in the tier 2, they're going to apply those fundamentals to fun and relevant problems. In the way we work on the tier 1 approach is by breaking the students into small groups and tackling the problems together. And also, this enhance communication and an ability to learn from peers. And we also take that approach outside the classroom, where they use tools like Piazza to interact themselves and ask themselves questions or ask questions to the instructors to further clarify things that were not clear during the class or the lab session. Okay, so the example for principal component analysis that we use as a toy example, we basically generate synthetic data that comes from a bivariate Gaussian distribution that us as instructors know what the covariance structure is, but the students don't. So basically, in order to reveal the underlying structure, which is exemplified here on the graph on the top right, where we have the two axes of the ellipse and the contours for the first and second standard deviations, is that they basically need to do a very simple rotation and then project to the axis to basically reveal the underlying structure. And this mantra of doing rotations and projections and basically decomposing the covariance matrix into those two operations are the fundamental principles behind PCA. So the take-home message of this short activity is to play around with rotations and projections, understand data variability and how that it's expressed geometrically. And I think the third point is actually the most important, is that matrices can be used to represent data and also to transform data. And it's this duality that is essential for most modeling and data visualization techniques. And then what we do is we pose them with a challenge activity where we ask them to make a data set and pass that data set to a fellow student, and they're going to use the same techniques we just discussed to reveal the underlying structure. So now I'm going to talk about the tier 2 approach. And in this case, I'm going to show an activity for doing PCA for image classification. And this is the fun part, at least from my perspective, and usually from the perspective of the students as well. So basically here I'm showing sorry, I lost track of the cursor. Okay, here it is. A data set that has handwritten digits from 1 to up to 0. And this is coming from basically a data set that was collected by people that wrote zip codes. And the idea was to do handwritten recognition for sorting mail. The images are 28 by 28 pixels, and therefore these images live in a very high dimensional space. And the task they're going to be doing is trying to classify the digits 1 from 7. So basically, we give them a data set that contain multiple instances of those 2 digits. And this is going to provide a chance to revisit rotations and projections. So here I'm just plotting the pixel intensity of 2 arbitrary pixels. And you can see that in this space, it's almost impossible to classify or separate or cluster those 2 images. And in essence, the key idea here is that there are more than 300,000 possible pairwise plots, and it's not clear which one to choose. So one choice that is very informative is to try PCA, because PCA captures the patterns of that have the most variance. So after performing PCA, we can see that the 9 images that capture most variances are shown in this graph, where the top left corner is the pattern that captures the most variance, and the one on the bottom right is the one with the less variance. So now that they find these patterns, they can project the data into the two first principal components and plot those projections, labeling the images. And the nice thing is, and in this new space, the images are easily, they form clusters that are linearly separable, and therefore we achieved multiple tasks. Aiding in visualization by finding the relevant dimensions in a multidimensional data set, and also building a classifier that will allow us to distinguish one digit from the other. So in essence, the learning outcomes of this activity is using PCA to reveal underlying structure and aiding in visualization and classification. It also provides a chance to talk about shortcomings, assumptions, and pitfalls of this technique, which is not applicable in all circumstances. And as I said before, it gives a chance to emphasize the different role of matrices, as matrices for storing data and matrices to transform data, so to perform those rotations and projections we previously discussed. And finally, from students' feedback, this 2-tier approach helps them to keep them engaged and motivated to learn, but at the same time being challenged because they have to deal with data they haven't seen before, and also provides a chance to improve their confidence and competency to use these tools in contexts that are not necessarily the ones we use in the classroom. Thank you.
Thanks. Oh, thank you, Daniel.
Mm-hmm.
I think I have to shut off this. Okay. Okay, so that was great, all 3 of you. I appreciate it. I think that those were pretty interesting, and I bet people are thinking about how they might apply your world to theirs, because even if they're going to teach exactly what you taught, how can they use some of the ideas or the code or whatever? So thank you. That was great. And so as I said earlier, so there's this community out there. And when I say that, I mean there are people like the people who just presented. There are other people on this call who have presented at events talking about teaching computation with MATLAB. There are people who have attended the workshop, and you saw those names on the website. And there's also a place you can go to join the community and participate in discussions or start discussions. And so if you go here and click on Join the Community, it will add your name to a list of people. And basically, you can ask questions just like you're doing in the chat. And we've often had, threads that went on for 10 questions. I've also seen threads offline, meaning they didn't go through the community site. They just started talking to each other. They, you, the faculty, all of us were having a conversation. It's much better if you can include everybody and everybody could see it. and that way anyone can participate and learn. But I'm letting you know that it's not just this webinar that provides you access. You can actually go and join the group, and because you've joined the group, you can then start conversations and you'll get answers. People are very good actually about responding quickly, and because I'm on the list, if there are things you want to know about MATLAB or the things that MathWorks can help with, I will look for those resources for you. So I encourage you to join. It doesn't hurt. Just click join, and it'll prompt you to, I think, give your name. So that's something to be aware of. The other thing that is worth knowing is that there are more sessions like this and more ways to get involved and think about your teaching and teaching plans and get help with those. In particular, there's an event called Earth Educators Rendezvous, and that's taking place in July. I believe it's in New Mexico. And I guess the deadline is Monday for early bird registration. So there'll be a session on MATLAB given by Frederick Simons on one of the days, and just general interesting ideas about teaching about the Earth, and this is obviously in particular for geoscience, related curriculum. But we're going to have another workshop like we've had. This will be the third year. Like I said, we had around 40 last year. We're looking to at least double. Actually, we're shooting for 100, and we're very excited about that because we're really going to work on curriculum this time. The idea is that it'll be a place where people can really bring their work and move it forward, move your course development forward there, partly because we'll have so many people to help you. So if you're interested, please email Rory. Anybody who signed up for this webinar, we already have your information, but if there are other people you know, if they'd like to be kept informed, then they need to email Rory so he'll know who they are. Okay? And so this is just a summary of the high level into what you've seen. As we said, the webinar will be posted on YouTube, but also the slides will be on the SERC site. But if you wanted to go find these things that you saw, besides all the links that are in the chat there, you could go in through the MATLAB tool sheet that we shared, and also go in through these different activities and that high-level view with the 4 different subsites, and again the community. So those are the things that are available to you, again, even after this, that you can peruse and learn from. And with that, I think we're ready for questions, if there are more than have been posted. And anybody can answer questions, anybody who's on the call. Randy Richardson is typing. Hi, Randy.
Yeah, so if other people have questions, please enter them into the chat or comments about MATLAB or your experience, and then we can get the presenters to talk about those topics.
May I quickly mention something that Charlie asked earlier if I implemented dipping layers, and I said no, but I forgot that I actually did.
Multiple attendees are typing.
Ooh.
That's what it says. So we're waiting for the question. Thank you, Alan. And again, thank you, Alan, Ben, and Daniel. Those were great. So Charlie says, what are the biggest challenges you find with your students learning to program? And who wants to take that? Ben, you were talking about some of that. Anybody else?
Yeah, I'm happy to answer some of that. So I think that one of the biggest things that students have trouble with is dealing with error messages, and they seem to think that it wasn't a real human who wrote the error messages, that the computer or the code somehow behind the scenes is sentient in its own, and so teaching them to deal with error messages, I think, is one of the biggest challenges. That when you can take the error message that comes straight out of the red text from your MATLAB command line, and you can just put that into Google, but you shouldn't try to reinterpret what you think it's saying. You should actually use the words. So I think that's one of the biggest challenges that our students face, at least.
And I see a question, thank you, Ben. I see a question from Randy Richardson who's asking, we have resources for getting started, but what are the best practices for dealing with a wide range of skills? So I'm going to take that one. I think the MATLAB on-ramp is a great thing to require students to do. It's, like I said, about 2 hours, and it would bring everyone up to the same level. Now, of course, if you've had previous experience with programming, you might find it easier, and if you haven't had any, you might find it harder. But at least you as an instructor would know that they did it, and they actually get like a certificate at the end, so they'd know that you'd be able to know, and they'd know that they finished. It has chapters. You could require all of the chapters or some. So I think if you want to level set, pick something to level set on. I'm recommending the MATLAB on-ramp interactive course, but other people may have other suggestions for what the startup set should be. Randy's typing some more, and Charlie's typing too. But that's my suggestion. Find a sort of, some people call it boot camp, and some people make it the first homework, and some people make it a prerequisite for the class. But I think if you could get to class 1 or 2, having established a baseline, that would be good. Another thing, since you're still typing, one of the things that Frederick Simons did in okay, I hear you, Randy. One of the things that Frederick Simons did, and so I'm not necessarily saying that somebody has to do on-ramp who knows already, but Frederick has a list of sort of like a checklist, and he has it online somewhere, but it's a list of all the things he wants people to know, and basically as he teaches, he has them add to this list, the students, of the skills they're gaining. So it could be that you could have everybody keep a list, and if people could check off items already because they already know, they wouldn't need to go and, build their competency, but maybe there's a list you want them to either use as a reference sheet or have them check off as they go, and as long as they're keeping up with the checklist, they're in good shape. Anyway, that's some of my suggestions. Other people may have others. Yeah, so Charlie said MATLAB on-ramp was good, and
we also use the MATLAB on-ramp in our boot camp. That's what we do on the first day. Make sure they all have MATLAB installed, working, and do the on-ramp, and just forcing them. It's true. It does take about 2 hours, so you do need to have an extended period of time to force them to do it in some cases. And
that's Ben who's speaking.
Yeah.
Okay. So you're hearing from Princeton. You're hearing from Toronto. That's Charlie. And I know other places do it. Yes, the on-ramp can be started and stopped. It can be started and stopped at any time, but it also has chapters. So you can do, sections. I forget how many. I should remember, but but they can take 15 minutes each, and you can, then come back. And it remembers where you are. It doesn't lose track. If you just type it. Sorry, go ahead.
Oh, I think Jack Herman's asked the question earlier. So I personally, so this is Anna, I personally feel that Fortran has too steep of a learning curve to actually get easily started, and I feel my students often already have a problem with how do we type easy, very simple computations, and if I have them import packages and compile, then I think it's going to get much harder. But so, yes, MATLAB is proprietary. Student licenses are not so expensive. And there are open source public domain programs that can actually interpret and run MATLAB code. Not maybe the most complicated, but some of the basic simple things. And so students that cannot, or people that don't have access to MATLAB could use that.
Yeah, I want to comment on your question about Fortran, Jack, because we use the term programming here sometimes, or computation we also use, and this has come up in the workshop repeatedly. We're not really trying to teach people programming, meaning in the sense of, if I was going to teach a programming class, do you use C, do you use Fortran, do you use MATLAB? That's a different question. This is really more about, everybody here may have different goals, I realize that, but the thing we're trying to answer here is, if you're trying to teach your domain, meaning geoscience or neuroscience or biology, and in order to do that effectively, your students need to be able to do computation, data analysis, visualization, etc. There are products that are much better than, say, Fortran at doing that. MATLAB is a great example. And so along the way, they're going to learn programming, but the goal is not to make them programmers. The goal is to make them good at computational biology. And that's, for example. So with that goal in mind, there are better packages than like Fortran. So thank you for providing Frederick's course notes. many people are typing.
And there's one more comment about Python, about using Python.
Right. So I don't know if anybody else wants to take that. I could just, I could give, sorry, go ahead.
Oh yeah, I can quickly mention. I would give a similar answer as before, that when you want to run Python, you have to use this import and all of those things. And I feel as a next step, for example, using MATLAB as an entry-level drug, if you will, and then on the next step, moving to Python would, I think, be a very good idea. But starting right away with Python, with the overhead of things you have to do before you actually go to the scientific computing, I personally feel is an added complication.
Yeah, so one of the things in many schools, we have something called a site license, or you might hear it called TAH, Total Academic Head Count, and we're trying to make access to MATLAB very easy and very common, because basically when push comes to shove, people will say MATLAB's preferable, like Alan just said. And so MathWorks is trying hard to make sure that people can get to it. And if they can get to it, it's generally viewed as the preferred tool. Plus, if you want to move on to things like simulation and model-based design and working with hardware, we also have the whole Simulink set of products for computer vision control systems. Ben was talking about dynamical systems. I don't know if you're familiar with Simulink. So if you're going to do that, then you're not going to want to be in Python. You're going to want to be in MATLAB and enable the use of Simulink. So I hear you. There are many choices and different reasons you'd pick them, but we're sharing some of the reasons here for MATLAB. So, other questions? We're 2 minutes away from the end of the hour. I don't want to keep people too long.
So there was an earlier question from Aaron about, is there a way to see what's involved in the MATLAB on-ramp? You know, is there a preview beyond what's on the short video?
Oh, I mean, I could bring it up here, but I think you should just start. Like, it takes 15 minutes to do the first chapter. So, and you don't have to spend that long. Spend 5 minutes. So, you just get going. There's no cost involved. So you just start, and it asks you questions. And does that answer your question? I mean, it's just online, and you start. You don't have to download anything. It's all on the cloud. Oh, you might have to give it a login, but there's no. It doesn't require you to have. Well, if you're yeah. So. Oh, well, you can just create a login, but presumably, if you're going to have the students use MATLAB, they're going to have they will already have a login, but you can create one. They can create one. But anyway, I can talk to you more, Erin, about this after, but the assumption is that you have a MATLAB that you'll be using. That the MATLAB on-ramp isn't going to be your MATLAB license. It's just going to be a training tool.
But I think it's free to create a login, right? Yeah,
but I'm just saying the assumption is that they will have a license that they'll be using beyond the on-ramp.
Speaking back, this is Ben here. Speaking back about the different languages, I think a lot of the tools that you'll see, all of the people at the workshop were working in MATLAB, at least somewhat. I don't think that the tools were just MATLAB tools. So I think that a lot of the practice activities, you might not be able to implement the code directly, but those kinds of ideas I think will be useful if you're working in Python or whatever your entry-level language is.
I see, I don't know your first name, sorry, McIlhaney. We have, there's a MATLAB, what do you call it? Sorry, MATLAB Online. So now if you have a license, you can use the cloud version of MATLAB. And I can't say that it completely matches what you're getting at here, but I think it's an easier to use system. Ye is typing, so maybe she's responding to Ye is from MathWorks. But But you might want to check out MATLAB Online, which is, like I said, a cloud-based version that students could use, and then you would know that all the students in the class were using the same version, had the same interface. Ye's commenting on something else in the chat, which is App Designer is the new GUI creation tool that is in MATLAB, so that's upgraded our application development or app development tools. So those are two different things, App Designer and MATLAB Online, which, two different topics.
Ben here again. I would also throw in the live scripts, which is a pretty recent advancement, but that takes care of a lot of these kinds of things where you input a new parameter or adjust a parameter and sort of see right away what that changes in the plot. And you can see sort of side by side your code and the graphs that it's generating.
Yeah. Yeah, we didn't cover features today. If we'd been covering features, we would have talked about App Designer, MATLAB Online, OnRamp, LiveScript. These are all great topics, but we were focusing more on the teaching tools specifically, meaning from the perspective of the, from the educators. But yes, these are all things that can be used. And some of the people who contributed activities to the site used LiveScript. They built their activity in LiveScript and other things. Yes, I agree. Maybe next time we'll show them. Yeah, he's typing. More typing. Yeah. Yep. No, it's okay. I'm fine with the typing. So yeah, check out Live Editor and LiveScript. We use those interchangeably. Live Editor is the place you make live scripts. LiveScripts is the sort of format, if you will, that you can publish your code in, and it looks much more like a published document. So all of those things, and you can use LiveScripts inside MATLAB Online, so you can have cloud MATLAB. Allowing you to create published documents, so you get the idea. Okay, so I don't want to keep people too long. It's 4:03. If people want to email us with any additional questions, that would be fine. If there's anything you didn't see that you want a link to, you can just ask us. We can do that, and as a follow-up, we'll probably send some links in the follow-up email to possibly to the things we're talking about here, so you can all find them.